So in this video, I will teach you how to find eigenvalues and eigenvectors of a matrix. So we have a matrix given and I will now teach you the procedure. But before we get to that, there are a few things that I want to tell you. There is something called as a characteristics matrix. Okay. And it is written as A minus lambda I. Okay. This is going to be a matrix and it is called as characteristic matrix. Well, A is the given matrix. So let us assume the matrix that is given to us as capital A. And this I is the identity matrix. So we already know that. And this lambda here is the eigenvalue. So what they're asking us to find out, this lambda is nothing but this eigenvalue. Now, once you write down characteristic equation, next is characteristic equation. Okay. And characteristic equation is the same thing, but you write it inside determinant. So it is determinant of A minus lambda I equal to 0. When you say it becomes an equation of a matrix and it's called as a characteristic equation. Now next is when you have a characteristic equation, you can find out the roots of the characteristic equation, which is this equation here. And those are lambda, or they're also called as eigenvalues. So plain and simple, that eigenvalue is nothing but roots of this characteristic equation. Okay. Now, once you find out lambda, after this is done, the next thing we'll do is find out eigenvectors. Now, I'll tell you how we find eigenvectors. Let me write that. For eigenvectors, we write it like this. The characteristic matrix we'll utilize, which is A minus lambda I, and then we'll multiply that with x and equate it to 0. Okay. And this x over here is called as eigenvectors. So this was just the basic overview of how things are over here. And now we will solve this question so that you'll understand what I'm saying even better. So we can just clear up this page first and first begin with the characteristic equation or eigenvalues of a problem and then eventually find eigenvectors also. So let us start. The solution will be, we will begin with writing characteristic equation, which is, as I told you, determinant of A minus lambda I equal to 0. Now, what happens is when you find A minus lambda I, A is this matrix, I is identity matrix, lambda is the unknown, those are our eigenvalues, and we are supposed to find them eventually. But then solving by this characteristic equation is going to be a difficult task. Okay. So instead of that, you can use this as a shortcut. So you can remember this is a shortcut of finding characteristic equation and the eigenvalues. And what we do is, instead of writing like this, we directly write down the equation, which looks like this. It is lambda cube minus S1 lambda square plus S2 lambda minus S3 equal to 0. This equation is going to be equivalent to writing like this. Okay. Now in this one here, S1, S2 and S3 are unknowns. Okay. I'll tell you what they are now. Look, S1 is sum of diagonal values. Okay. What are diagonal values of A? You have to sum them up. 8 plus minus 3 plus 1. That's going to be 8 plus minus 3 plus 1. And the value here is 6. Now for S2, now S2 is sum of minors of diagonal elements only. Okay. So diagonal elements are 8, minus 3 and 1. So we have to find out minors of all this. Let me explain how the minor works. So if you want to find out minor of 8, you have to hide this column and hide this row. Okay. Now whatever you see is the minor of 8. Very simple. So let's write down that it is going to be determinant of, yes, you'll write determinant, minus 3, minus 2, minus 4 and 1. Now that's the minor of 8. The next you have to find out minor of minus 3, hide this column and hide this row. Okay, row and column of that element we have to hide. Now you see 8 minus 2, 3, 1. Well, that's the minor of this element. Okay, let me write that. It is going to be 8 minus 2, 3, 1 plus, now last is this diagonal element. So to write down minor of this as well. So we will hide this column and this row. So you see 8 minus 8, 4 and minus 3. Let me write that. It is 8 minus 8, 4 and minus 3. and let us solve these determinants and quickly write down the sum of that is going to be S2. So it is minus 3 and this is minus 8 plus, let us solve, just cross multiply these two, 8 plus 6, and then for this one here it is 8 is a 24 minus 24 plus, this is 8 4 is a 32, and then S2 is going to be, this is minus 11, this is plus 14, and then this value is going to be plus 8. So if I sum them up, and the answer is minus 11 and 14 is going to give me 3, and 8 and 3 is going to be 11, right? So S2 is 11. I found out S2. Now next is S3. Now S3 is nothing but determinant of A. So given matrix, you will simply take a determinant, and that is the exact value of S3. And to find determinant, you can use a calculator. It will directly give you the answer. And if I find determinant here, this value is 6. Okay. Now as soon as you get S1, S2, and S3, which is 6, 11, and 6, let's put them back in the equation. So now this equation here will become that's lambda cube minus 6 lambda square plus 11 lambda minus 6 is equal to 0. You see, we got a nice characteristic equation. It's a cubic equation. So when you have a cubic equation, you will have 3 roots. Okay, so let me write down the roots. The roots of characteristic equation are lambda. Okay, you can use calculator and simplify and find out the roots here. The roots are 1, 2, and 3. And now these roots itself are called as eigenvalues. Okay, so we have done one part of the problem. We have found out eigenvalues already. The next thing we want to do is find eigenvectors. Now for every value, every root, every value of lambda, we will have we will have corresponding eigenvector. So how to solve that? Now we will see that. So the eigenvalues that we have obtained are, one was 1, 2, and 3. Okay. Now for every eigenvalue, we will have to find out the corresponding eigenvector. Now for eigenvectors, we will need to use a matrix A minus lambda I times X is equal to 0. Please note that here X is the eigenvector. Okay, that is what we have to find out. So how does this work? First of all, let us write down A minus lambda I. The A minus lambda I value is going to be, well, this A is the given matrix, which is 8 minus 8 minus 2, 4 minus 3 minus 2, and 3 minus 4, 1. That's A minus lambda I. I is 1, 0, 0, 0, 1, 0, and 0, 0, 1 times X, okay, equal to 0, right? Now let us multiply this lambda inside. How does this work? When you're multiplying lambda, okay, to this bracket, it is lambda into 1 is going to be lambda, okay, then lambda into 0 is 0, lambda into 0 is 0. So just like multiply everything, this 1 will become lambda, and everything, all the zeros will remain as it is, because you just multiply with every element, and then that's how the lambda gets multiplied to this matrix over here. And well, we have to do the subtraction. Now how does the subtraction work? I have to subtract 8 minus lambda. It's always point by point. The value of first column and first row, this 8, will get subtracted by first column, first row, this lambda. So it becomes 8 minus lambda. Okay, let's write that. So it becomes 8 minus lambda, but then minus 8 minus 0 is just minus 8. And then minus 2 minus 0 is just minus 2. I hope you get the point that everything else will remain as it is, like only the diagonal values will change. So this will become minus 3 minus lambda, and this will become 1 minus lambda. This is 1 minus lambda. Minus 2 will remain as it is, 4, 3 minus 4 times X is equal to 0. Let me give this equation as a equation, let's call this equation 1. Okay, so we are now going to use equation 1, and using equation 1 we will find eigenvectors. Now see how that works. First of all, let us begin with the case 1. Now for case 1, let's say for @lambda is equal to 1. What happens if lambda is equal to 1? Okay, we will substitute this in equation 1. So if I substitute lambda equal to 1 here, so now this lambda value, okay, you will replace by 1. So this will become 8 minus 1, minus 3 minus 1, and 1 minus 1. And well, that's the only change you will have. So if you substitute lambda in this equation, this one here, okay, in this, if you substitute lambda equal to 1, you will get this as 7, then minus 4, and 1 minus 1 is 0. Only the diagonal values will change, right? Minus 8, minus 2, 4, 3, minus 4, minus 2, all of them as it is. Now this x over here is nothing but a column matrix. Okay, so if you know the basic matrix theory, that if you're multiplying this with a column matrix, let us call this as, say, x1, x2, and x3, and let that be equal to 0. Now notice that your capital X is nothing but the eigenvector. It's already written over here. And we are supposed to find out eigenvectors. That means we are supposed to find out this. That's what we are supposed to do right now. To simplify this, you can use many techniques. Okay, one of the simplest way to solve this is the Cramer's rule. So let me write down the Cramer's rule. Now we've done this in school, but let me still remind you how this works. Okay, so you can take any of the two row. Listen to the procedure carefully. Any two row, you can take first and second, or second and third, whichever one you want, or first and third. Let me take these two rows. Okay, so if I take these two rows, okay, to apply Cramer's rule, it is written like this. It is x1 divided by a determinant is equal to negative x2. Don't forget, negative x2 divided by determinant is equal to x3 divided by a determinant. Okay, and now if we decide to take these two equations, these two rows, first and second, for x1, look, for x1, for the first one, you will take determinant of these two. I hope you remember this also. It is minus 8, minus 2, minus 4, and 3. So minus 8, minus 2, minus 4, and minus 2, right? And next is for x2. When you're finding for x2, you will take 7, 4, and minus 2. So you will take 7, 4. This is minus 2 and minus 2. Now for x3, you will have to hide this and you will take this. So it is 7 minus 8, 7 minus 8, and this is 4 minus 4. So we have to just simplify these determinants. Okay, it will become x1 divided by, this is 8 to the 16 minus 4 to the 8. So 16 minus 8 is 8. Then this is, let me keep minus x2 divided by, this is 7 to the 14, minus 14, and this is 4 to the 8 plus 8. Minus 14 plus 8 is going to be minus 6, right? And then for x3, you will write it as x3 divided by, let us simplify this, 7 4s are 24, that's minus 24 and plus 32, 8 4s are 32. So that is going to be minus 4. Okay, now once you get these numbers here, we can simply assume that, you know, we got this equal to this equal to this. We can assume this, let this be equal to k. Okay, so if I compare the first one with this, then the second one with this, and the third one with this, because they all are equal, I should get the value of x1, x2, x3. I'll show you how. So I'll say x1 divided by 8 is equal to k, and x2 divided by 6, this minus will cancel out, is equal to k, and x3 divided by minus 4 is also k. So you will get x1 is equal to 8k, x2 is equal to 6k, and x3 is equal to minus 4k. And look, x1, x2, x3 are these values here. Okay, I can simply substitute them back here, and then this was our capital X, and capital X is the eigenvector, so we found eigenvector. So let me write down the eigenvector finally. The eigenvector capital X is equal to, it is x1 is 8k, x2 is 6k, and x3 is minus 4k, right? You can just take k out, you can take even 2 out. So let me take 2k out, and then it will become 4, 3, and 2. All right. So you can always neglect this constant here. Eigenvectors are not unique. So you can just write down the main factors here. So it is going to be 4, 3, and 2. Now this is the corresponding eigenvector of the first eigenvalue. For lambda equal to 1, we got eigenvectors as 4, 3, 2. Finally, we'll write down the answer as well, but I hope you still followed the procedure. So now I'll write down the eigenvector for 1. So let me make some space here. Okay, and let us write down the eigenvector value that we've just got. It's like this. See? Well, for lambda is equal to 1, we have found the eigenvector as 4, 3, 2. Okay, and once we get lambda equal to 1, now we have to try for lambda equal to 2. So all I have to do is I have to put lambda is equal to 2. Now that's going to be my case 2. And the solving is going to be very much similar. So I'll put lambda is equal to 2 here. So this becomes 2, this becomes 2, and this also becomes 2. So only these three diagonal values will change. Everything else will remain just the same. So if I put lambda is equal to 2 in this, so how are the changes? 8 minus 2 is going to be 6. Let me modify this only. Now for case 2, this is 6. And then this is minus 3 minus 2 is going to be minus 5. Right? And then this is 1 minus 2. 1 minus 2 is going to be minus 1 over here. Okay. Now, once again, you can use Cramer's rule, okay, and simplify. So let me erase and do this Cramer's rule a little bit. You can take any two equations. Once again, take first and second. And let's just see how that works. So the procedure is going to be very much similar. So why not use the same structure? So let us simplify this and let's see what we get. Okay, so now this will be for x1, for the x1, for x1 you will take these, right? So we'll take minus 8 minus 2 minus 5 minus 2. So minus 8 minus 2 minus 5 minus 2. And for x2 you will take 6 4 minus 2 minus 2. 6 4 minus 2 minus 2. And for x3 you will take 6 minus 8. 6 minus 8, 4 and 5. So if you solve them, you will get x1 divided by, if you simplify this determinant, the value is 6. Then if you simplify this one, the value is minus 4, and then the minus cancels out. And for x3, it is divided by 2. It's very much similar procedure. Simplify this determinant and you equate this with k. So you get x1 is equal to 6k. x1 is equal to 6k. Now the minus will cancel out and x2 will become 4k and x3 is 2k. And the small x1, x2 and x3 are these values here. So we will put them back here. And that's how going to be your eigenvectors. So capital X, I'm writing down this eigenvector here, is 6k, then 4k and 2k. Of course, I can take 2k common. Okay, we just write down the multipliers here. This will be 3, this will be 2, and this will be 1. And now that's the eigenvector for the second one. So let me write down the second eigenvector. Now this I got corresponding to lambda 2. Look, I took lambda is equal to 2. And when I did that, I got this eigenvector, which is 3, 2, and 1. That's the eigenvector for 2. Now in the case 3, of course, we will take the next lambda, and lambda is equal to 3. Let me still modify more. If I have lambda equal to 3, Okay, that will be case 3. 1, 2, 3. Okay, and when I say lambda is 3, 8 minus 3, now this number will be 5. Okay, and minus 3 minus 3 is going to be minus 6. So this number will be minus 6, and 1 minus 3 is going to be minus 2. So this will be minus 2. Okay, so once I get these values, accordingly I'll again use Cramer's rule and simplify this more. You can take any two rows. I'll take first and second, and let us simplify this. So let me clear these things. So for x1, it is minus 8 minus 2, minus 6 minus 2. I'll take these values. For x2, it is 5, 4, 5, 4, and minus 2 minus 2. And for x3, it is going to be 5 minus 8, 5 minus 8, 4, and minus 6. And you simplify this so that you'll get 8 minus 6 minus 2 minus 2. Yeah. So simplify this, you'll get x1 divided by 4. And this is x2 divided by 2. And then x3 divided by 2 as well. And then therefore you write down x1 is 4k, x2 is 2k, and x3 is also 2k. And therefore your capital X, the eigenvector, is going to be 4k, 2k, and 2k. So you can take 2k out, and then you just write down the multipliers inside. So it is 2, 1, 1. And now that is the corresponding eigenvector for 3. So the eigenvector for 3 eigenvalue is 2, 1, 1. This is one basic problem where I showed you how the working of eigenvector, eigenvalues and eigenvector is done. And I hope you followed this whole procedure. So there are some variations, there are some advanced methods. Based on this, we can do many things about matrices. All that is coming up. In the next subsequent videos, we will see all of that.